Here is the first question. We are going to see several plots. And then every one of these plots show just one solution of some differential equation. So notice that all these differential equations are going to be second order linear differential equations with constant coefficients, but maybe homogeneous, maybe non-homogeneous, right? Okay, so the first thing is which of these plots shows a solution of a homogeneous differential equation? The question is to pick one or more options. And basically, for homogeneous differential equations with constant coefficients, it looks, well, the form is y double prime plus by prime plus cy is 0. And then, depending on b and c, there are only finitely many different cases. So there could be oscillations, or there could be a combination of exponential functions. So here we always see oscillations, so it's got to be oscillations. But then whenever it is oscillations, then there could be oscillations of exponentially decreasing magnitude, oscillations of exponentially increasing magnitude, or oscillations of the same magnitude. And well, we only see one plot like this, is plot B. So here we see oscillations of exponentially increasing magnitude. So by the way, so it means that here b squared minus 4c is negative, the discriminant is negative, and b is also negative. So if b is positive, then oscillations would be decreasing. Right? So compare to plot F. In plot F, the magnitude of oscillations is increasing linearly, and in plot A, it is increasing but then stabilizes. So it is something different. Which of these plots shows an undamped resonance? So pick one option. So the model for undamped resonance is something like T sine T. So undamped resonance means oscillations of linearly increasing magnitude. And here we see oscillations of linearly increasing magnitude. So this is option F. Which of these plots shows a damped resonance? So damped resonance means that there exists a viscous force that prevents oscillations from magnitude from growing indefinitely. So oscillations should grow. Initially, the oscillations should become bigger, but then they will stabilize. This is case A. So oscillations are growing at first and then are stabilizing, right? So notice that in C, oscillations are kind of become bigger than smaller, bigger than smaller. So it's not that. So which of these plots shows non-resonance driven vibrations? Wow, okay. So non-resonance but driven vibrations. Okay, so non-resonance driven vibrations. So basically, this is whatever remains. So we have non-resonance. So in A we have non-resonance. In F we have non-resonance. In B we have something that is not driven. So driven means that the right hand side is not zero. Right? So driven, the word driven means that it is M Y y double prime plus gamma y prime plus k y is 0. This would be free vibrations. Driven means that the right hand side is not 0. Okay, well, it's not B, so but the rest seems to be the right choices. So C, E, and D are all non-resonance driven vibrations. So whatever remains. So maybe just for your information that D is damped and E is undamped and C is also undamped. So how do I know that? Because E and C are periodic motions and D is not a periodic motion. So you see, initially in D we have some kind of two types of oscillations, and then the first type of so one is kind of the big sinusoidal wave, and another is little oscillations around that big sinusoidal wave, but those little oscillations eventually disappear, and we only in the end we only have just like the big sinusoidal wave. This is the um, uh, this indicates the presence of damping force. So initially we had both the driver and the internal vibrations of the system were present, but then as time goes by, the internal vibrations dissipate and we only see the driver. So this is the damped oscillations. Maybe let me show you a few cases. So this is undamped oscillations are like the combination of one sinusoidal wave and another sinusoidal wave. Well, it doesn't have to be sine. It could be cosine instead of sine. It doesn't matter. So it could be cosine. So as long as two waves are kind of are present there, and both of them remain there for, well, like forever, then it means that the whole thing is undamped. But if we introduce a little bit of damping to say, if say 3 cosine 3x is the internal oscillation, let me introduce some damping here, say something like this. Then initially, you see for the driving force is kind of is not sufficiently strong for us to see it, right? And then as time goes by, we kind of see some sign of the driving force, but then as time goes by, further and further, the internal oscillations disappear because they're killed by this damping, and now we only see the driving force. Okay, I hope this is clear. Well, and now the last question: which of these plots show undamped driven vibrations? So as I already explained, well, question D is about all non-resonance driven vibrations, and question E is about undamped driven vibrations. So here we should include those undamped non-resonance cases from the previous question, and also there should be the resonance undamped resonance because it is also a driven vibration. So then now the answer is C, E, and F.